Hello math people, it's Mr. Ray here with our next lesson in grade 11 University Math. We are working on the functions unit, so we're going to dive a bit deeper into our new world of functions. If you remember the first three lessons, we looked at things like, well, what is a function? How do you know it's a function compared to just being a relation? We defined what domain and range are for a function. We also looked at function notation, which is a very important new way of writing equations in lesson 2. And previous lesson we looked at what we call base functions. And these base functions, we're going to be using those for the rest of the unit. Those are basically parent functions that sort of the most common types of functions, and how we can use what we're going to learn in the next 3 or 4 lessons to start off with the parent function and create an infinite number of a family of functions, the child functions. And today we're looking at the first type of way we can change these parent functions. The lesson's called Transformations 1. So the way we change the look of the parent function to become a child function or a family of functions. There's a few ways we can do it. First of all, we could look at the definition of transformation. Now, you saw this in grade 10 when we were looking at quadratics. We transformed the graph of y equals x squared using translations and stretches and compressions and reflections. Well, we're just going to extend that concept into not just quadratics, but into all the types of functions we looked at with the base functions. So it's a more generic approach to how we can modify functions. So this lesson, Transformations 1, just looks at translations. And the translation is a transformation that results in a shift of the original figure without changing its shape. So when we talk about shifting it, we're going to be moving it left or right or up or down. So it's like taking a picture of the original parent function or any function and just shifting it around up, down, left, right. Okay, and like I said, we've already done this with quadratics in grade 10, so it's just kind of extending that concept. So and here's that same definition again. So we're not changing the shape of the graph when we do a translation. We're changing the position. Where is that shape on the graph? Okay. Now, unfortunately, when you learned quadratics in grade 10, we had 2 parameters that we used, h and k, that h defined the horizontal shift and k defined the vertical shift. And so what we're learning today is very, very similar to that. Unfortunately, and I don't know why math people do this or textbooks do this, we're changing the name of the parameters. So instead of using a k for saying it's going to shift up or down, we're using a c. Okay? And I wish they just taught you this in grade 10 when the textbooks called the k value a c value. And they've also changed the h value to a d. So h changes to d, k changes to c, but basically everything else we've learned about that still applies. So if you have a graph, and now you notice we're talking about function notation now. If you have a new graph or new function g of x, which is just taking an original function f of x, which in our case will be a base function, and we add the value c. So whenever we do that, we know that's just taking the original graph, if we were to graph this graph of f of x, and we're moving it up or down that c units. Now c depends, if it's negative we move down, if it's positive we move up. Okay, so very, very similar to what happened with k when we were working with quadratics. And similarly we have, if we subtract d from x, okay, that actually d defines a horizontal translation. Okay, now d, if we put it in this form, x minus d, remember quadratics, that h value is a little bit funky because you sort of had to switch the sign to understand what it was doing. Same thing happens here. So you really should be writing it as x minus d to get the correct value of d. And then once you do have that correct value, if d is positive, you're shifting it d units to the right. If d is negative, you're shifting it d units to the left. Okay, so again, very similar to what we did in quadratics. We're now applying it more generically to all functions. Okay, and a sketch of the graph of any transform function can be created by transforming the related base function. So that's what we're going to be doing when we graph. We're going to take some of the key points, the base points of the original base function, and we're going to be applying whatever translation we see in the new function. Okay, and if you put the two together, like we talked about, f of x plus c, c is a vertical translation, or f of x minus d in brackets, d is a horizontal translation, we can put those two together. So we could actually do both at the same time. So this is a lot like your y equals ax minus h squared plus k. Obviously, we've changed the h to a d and the k to a c. And instead of using x squared, we've got this f, which would refer to the original base function. It could be, the original function could have been quadratic, x squared. It could have been, square root, could have been any of those five. So it's probably a little confusing right now, so I think we should do some examples just to get the hang of what's going on here. Okay, so you can see we've got a little graphing area over here, and the question, example 1 says, given a function f of x, sketch the graph of g of x by determining image points from the original base points. So when we defined those base points in the last lesson, they're coming out now. So we have to figure out what the base function is and then recreate those base points, and then we're going to transform those base points based on what type of translation is happening here. Okay, so the base function, they're giving it to us here, f of x, and I'll try to keep it this way. I'll try to name the base function f of x and then the transform function g of x. It's not always going to happen. I know the textbook doesn't always do that, but I think it's good to start off that way, where f of x is the base function, g of x is the transform function. So what they're telling us here is the original base function was x squared, just like in grade 10. And what we're doing with g of x is we're taking the original f of x function and we're adding 4. So I could just replace f of x with x squared to get the full expression for the function. So f of x is x squared, so it's just g of x equals x squared plus 4. So these two mean exactly the same thing. It's just written in a slightly different way. This version up here basically relates it back to the base function. What are we doing to the base function? And this is just the complete function without a reference back to the base function f of x. Okay, now if I was to look at this and compare it back to this kind of generic translation template here, I could see that, and you could actually use this version too, you could see that this 4 value, that's actually our C value. So I can put an arrow there and say, well, that's what C is. Okay, now what I'm going to do here, and I probably should have given more room here, maybe I'll just zoom in a bit so it looks bigger. Okay, I'm going to put the base points of f of x here. So I'll put f of x above to show that this is a table of base points for f of x, and over here these will be the transform points, which would be points on the graph of g of x. Okay, so f of x in this case, remember that the base function was x squared, so our base points, and I'm just going to put y equals x squared instead of f of x. I don't want to confuse you too much. This refers to the coordinates. All right, so if you remember, those points were -2 up to +2. And when you square those, you get 4, 1, 0, 1, 4. Okay, so those would happen. You'd have these here regardless of what you're doing to the base function, as long as the base function was x squared, quadratic. Okay, so those are the original points. And remember that 0, 0 point, that was the vertex, the one in the middle. Okay, now I'm going to put my x and y values here, and you can, if you remember the c value 4 here, well, the c, since it's a vertical translation, it means you're adding that value to the y coordinate for each of the original points. So what I'm going to say here is the x values stay the same as the original f of x function. We're not doing anything horizontally, but the y values we're actually going to add the value of c, which is 4. So I basically put it at the top of my column here. I'm going to take the original y value from here and just add 4 to it. So that's 4 plus 4 is 8, 1 plus 4 is 5, 0 plus 4 is 4, 1 plus 4, and 8 again. Now, what happens when we transform these base points? The vertex is still the vertex. So that middle point, 0, 4, is our new vertex. Okay, so now all we'll do is take those 5 key points. I'm going to start off in the middle with 0, 4. So 0, 4 would be right here. And then I've got -1, 5. So -1, 5 is here. And then I've got 1, 5 to the right. Remember, these are like mirror points. Now, unfortunately, these 8 points are a little bit off the graph, but I'm going to, just pretend my graph's a bit bigger than it is. So I've got -2, 8. So 8 would be about up here. And then +2, 8 up here. So you can see those 5 base points, they give me a good idea of where that parabola is. And I know that middle point was the vertex. Now, whenever I draw a quadratic, I like to put a little cup where I know my vertex is, and it points sort of towards the other points, just so when I do my sketch, it's a smoother looking curve. I don't like to connect the dots parabolas. Okay, so there's our graph, and this is the function g of x. Okay, so hopefully that makes sense. We found out the original function, base function, was the x squared or quadratic function. We put those memorized base points for y equals x squared, or just memorize these. Then we figured out from the new transformed equation the values, in this case the value of c, or the value of d, which this one didn't have. Well, the value of d was 0 because we're just adding 4. We weren't changing the x coordinate at all. And then just modify the table of values for g of x for those new transform base points, and then just put those 5 points on, and there's our sketch. Okay, so let's go on to another function here. Okay, so this time they're telling us that the base function we're working with, we're starting with the square root function. You can tell by the square root symbol, obviously. And what we're doing to the base function is, this time it's a little different. We're not adding 4 to f of x. We're changing the input from x to x plus 4. Okay, so what I'm going to do here is I'm going to also rewrite the expanded version of g of x, just like we did on the last one. This one's a little bit trickier because it has to do with the input. So if the original function was square root of x, f of x, the square root of x, but now I'm changing the input from x to x plus 4. That means my new function is the square root. So I'm changing x to x plus 4. So the x plus 4 is under the square root because that's where the input goes. Okay, so again, these two are the same functions. They're just written in a different way. This is referring back to the base function, what's happening, and this is just the, the expanded version of the new function. Okay, so again, I'm looking at this. I want to figure out what my C or my D value is, and I can tell by looking at this. Well, this is actually either one. You could pull out your value of C or D here. I can see that basically I'm not adding anything to the end of this outside of the actual f of x. So my D, in this case, my C value is 0, but my D value comes from here, or here. It's the same place. And remember from the first page here, that little funky thing that happens with inside the brackets there. If we want to figure out what D is, it has to be written as x minus D. Okay, so this is x plus 4. So what would D be to make this x plus 4? D would have to be negative 4. And then if I wrote x minus D, it would be x minus negative 4, which would be x plus 4. Just remember, you got to flip the sign. That's probably the easiest way to do it. So there's my D value. Actually, it'll maybe do this over here so I can have a bit more room. D equals negative 4. And I didn't put a C value, but we did talk about it. There is no apparent C value, which means by default, if there's no C or D value, the default is 0 because it's moving 0 units. Okay, so again, I'm going to do my base points. This time I'm doing my base points for the square root of x. So I do my table here. So x and y equals square root of x. And if you remember those points, it was 0, 1, 4, 9. Just because I like to have nice integer, or once I take the square root of a value, I wanted to have the nice integer results. I didn't want to have decimals that never ended. So that's a good, and remember that 0, 0 point, that was an end point. It didn't, the curve or line didn't extend beyond there, and it went out in this direction forever. Okay, so if I'm looking at the base points, or the transform base points for g of x. So this time, since I have a D value, that's going to affect the input because it's moving it left and right. That's the x value that it's affecting. So what happens, just like last time, well, sort of like last time where I added 4 to the y coordinate from my base points, this time it's going to affect the D value is affecting my x coordinate, and I'm subtracting 4. So I'm going to take the original value of x from this table, and I'm going to subtract 4 from it. And the y value does not change at all because there's nothing affecting the vertical. There's no vertical translation in this case. Okay, so if I just subtract 4, 0 minus 4 is minus 4. 1 minus 4 is negative 3. 4 minus 4 is 0, and 9 minus 4 is 5, and these values here remain unchanged. So 0, 1, 2, and 3. Okay, so now we've got some transformed base points that we're going to use to do our graph of this transform function. So start off with negative 4, 0. Okay, and remember what I said here. That was our special point. That was our endpoint. So when it transforms, it's still the endpoint. So that value there is like the curve is going to end right there. Okay, then I had negative 3, 1, 0, 2, and 5, 3. Okay, and it keeps going in this direction, but it stops right here. So I'll just try to do a nice sketch of what that looks like with my arrow going that way. Don't forget to put the arrows. Obviously for this one it's extremely important because you want to show that it doesn't go past here, but it does keep going infinitely beyond this point. Okay, so that's how we take the transform function of square root of x. This time it had a horizontal shift, which turned out to be a shift of 4 units to the left. And you can see that's really what's happened here. The original graph started here, and now the whole thing just shifted to the left horizontally. Okay, let's try some more. Zoom back in a little bit. Okay, so same kind of idea here. Little bit more difficult, but same concept. For each function, describe the transformations from a base function, first by using function notation and then using words. Transform the function of f of x to sketch the graph of g of x and state the domain and range of each function. Okay, I think we'll just state the domain of the transform function. We've got domain and range of the base functions on the last lesson. Okay, so this time they just gave us g of x. So we have to figure out, well, what was the base function for this? What was the base function of g of x? So there's a few clues you always look for, okay? For example, if it was a square root function that was the base, you would see a square root symbol. If it was absolute value, you'd see those two bars somewhere on the right side. If it was the reciprocal function, you'd see an x on the bottom of a division bar. If it's a squared function, quadratic, you'd see a square here, just like this one. So you can tell just by looking at which of the 5 base functions is this. It's the x squared function. So I can actually put that up here just in case I need to know. So the original base function of this transform function is f of x equals x squared. Okay, now what I'm going to do is I'm going to pull out the values of d and c, if there are any. So remember, it would look like, I'll just rewrite it up here once so you remember, g of x equals f of x minus d plus c. Okay, now I haven't written this yet as to relate it back to f of x, but I'm going to do that right now. So this would be the second version of g of x written in terms of f of x. So the way we do that, I'm going to start off with my f and then my bracket, and then ask myself, what's the new input for f of x based on what I have here. And you can see instead of just squaring x, we're squaring x plus 5. So in this case we've got x plus 5 as our input for x squared, and then at the end here we have our plus 1. Okay, it looks really similar. I've just replaced the squared with the function f, which is a squaring function. Okay. Now from either one of these, I could now pull out my values of c or d, or d, and I can tell, well, let's do the easy one first. You can tell that c is equal to 1, and there's also a d value because it's inside the brackets, and remember we have to flip the sign to get the correct value of d, so d would be -5. Okay, now they also want us to write out, describe the transformations, and this is going to be important. You did this in grade 10 for quadratics, and for me it's very important that you use the correct math terminology. I don't want you to say it's moved 3 units up or shifted 2 units to the left. Okay, I want you to use the verb translated, and so for this So for the transformations, and if you want to be a little bit more descriptive, you could say from f of x to g of x. So what did we do to f of x, this function, to make it become this function? Okay, so all I'm doing is that I'm interpreting what c and d actually mean. So start with d, just usually we talk about horizontal first. So the fact that d is -5 means it's been translated 5 units left. Okay, and notice we didn't say -5 units because the -5 is actually our hint that that gives us the left part. So we basically strip that off when we're talking about how many units up or down, left or right. We never put negative units for that. Okay, and then for the c value, remember when c is positive, that's translation up that many units. So in this case, it's also translated 1 unit, and because it's positive, it's up. Okay, so that's what they mean by describe the transformations. Okay, now you could, if you wanted to, I'm totally fine with this, you could combine these two statements into one. You could just say translate 5 units left and 1 unit up. Okay, and the order you do these, at least in terms of the description, doesn't matter. Okay, you could put the up first or the left first. It doesn't matter. Okay, so now what we're going to do is kind of what we did in the last example. We're going to start off with our base points for f of x, which is the x squared function. So we've already done this on the previous page. It's important to label these boxes with the function you're talking about. So f of x, again, -2 to +2, 4, 1, 0, 1, 4. Gets very, after a few of these, you'll never forget them. Okay, now g of x we're going to put over here. Now, so this time we've got two things going on, unlike the last example. We've got a c value and a d value. So all we're doing is combining both of these things at the same time for the first time. So remember, the d value is, we did that up here, right? When we had d equals -4, we subtracted 4 from the x value. So same thing here, except this time we're subtracting 5. X minus 5 because d is -5, and because c is +1, well, that's what we add or subtract. That's what we add to the y value. So this is going to be y plus 1. And we take the original base values here. So I'm taking these x coordinates from the base points, and I'm subtracting 5. So I got -7, -6, -5, -4, -3. Okay, and remember, 0, 0 is always our vertex, so whatever that point transforms to is our new transform vertex. Okay, and then here we're adding 1 to these values. So I've got a 5, a 2, a 1, a 2, and a 5. So those are the 5 points we're going to use to sketch our function g of x. So I like to start with the vertex just so I know where this function will be centered. So -5, 1. So that's my vertex. I have -4, 2. So it's going up. You can tell that now. I also have -6, 2 on the left. And then -3, 5 goes up here. And -7, 5 over here. So you can see there's my vertex. Do my sketch with my arrows at both ends like that, and there's my function g of x. Okay, so oh yeah, we also had to do domain and range. So I'm gonna do this looking at the graph. So the domain of f of x, well, remember, and you could take a lot of this information from our information from our base functions from last lesson. Any quadratic function, the domain is all real numbers. Doesn't matter how we transform it, this will always be true. Doesn't matter how much I shift it left or right or up or down, it's still all values of x are possible for this function. Now, if you remember, the range for a quadratic function is limited, but we still start off with, this time I'm going to say g of x. G of x is a real number, any real number, but, and you can tell from the graph here, g of x has to be greater than or equal to 1. You can tell that from the graph because anything less than 1, there's no point on the graph for that. Oh, sorry, I guess you weren't seeing that. So domain x is any real number. Anything goes. Range g of x is any real number, but g of x has to be greater than or equal to 1. Now, you can actually relate this back, well, at least for this function. If I wanted to know what number goes there, well, that's going to be the c value. Okay, but it's always safest to look at the graph or a sketch of the graph and say, okay, what's my new range for this quadratic? It's either going to be greater than or equal to a value or less than or equal to a value, and that value will always be the c value, because if you remember, that's our previously known k value, which gave us the y coordinate of the vertex. Okay, all right, let's do a couple more of these, taking a journey through the different base functions. So we've looked at the square root function, we've looked at quadratic a couple times. Excuse me. This time, just like we did last time, we have to figure out, well, what was the base function here? And if you remember my hints, how to know which base function this developed from, well, the fact that the x is on the bottom of a division bar, that tells you the original function was f of x is equal to 1 over x, the reciprocal function. Okay, now this one's always a little tricky. I'm going to put brackets around here. So if I want to change g of x to be written in terms of f of x, okay, this one's always a little tricky, so don't get too alarmed if you're not getting it at first. So the first thing I look at is, did I change my input that I would use? Instead of using x, what did I use? And you can tell that by, well, first you find the x, which was on the bottom. What are we doing to x? Well, we're adding 3. So you compare this. Don't look at the -7 yet. How did we change our input? We changed our input. It's basically f of x plus 3 now. Okay. So we took our original function 1 over x, and we changed the input from x to x plus 3, so it's now 1 over x plus 3, but then we also subtracted 7. So we put the 7 after the function notation part here. Okay, so again, these two are the same function, g of x, they're just written in slightly different ways. You should be able to get one from the other. Of course, in order to go this way from here to here, you have to know what f of x originally was to be able to do that conversion. But they will represent the exact same function. Okay, now from here, this should be a little bit easier. We want to pull out our values of c and d. So remember, the c value is found to the right of the function notation or to the right of the 1 over whatever it is. So in both cases, that's a -7. And the d value, we can see the new input is x plus 3. But remember, we have to flip the sign. So it's not +3, it's -3. So those are our two values of c and d. If we write those as transformations, like the description of them, And this time I'll put them together just to show you what I meant. And it doesn't matter which one you consider first. You have to use the word translated. So if I start, let's go with the C first. So that means 7 units down. And then the D being -3, that's the horizontal translation, and that -3 means to the left. So, and 3 units left. Okay, so let's do our tables. So you remember this one was a little bit, remember the graph of 1 over x? It had the 2 branches, and it also had 2 asymptotes, which made it quite unique compared to the other 4 base functions. So if I'm looking at my f of x, so my x and y equals 1 over x. Remember I had the 2 parts. I had sort of the negative branch and then my positive branch. So I had 3 points on both sides, both on each branch. So for this branch, once you do the reciprocal, and this is taken right from the base key base points that we did in the last lesson. So 1 over -1 is still -1. 1 over -0.5 is -2. Positive 2, 1, 0.5. Okay, and then we're going to transform these points using our C and D values that we just extracted. So all I'm going to do is modify each of these 6 coordinates. So what are we doing to the x coordinate? Well, that's from the D value. So we're just adding that to our x. So it's going to be x plus -3 or x minus 3. And then for the C value, we're adding that to the y coordinate from our base points. So that's going to be y minus 7. Okay, so it's always good to do one coordinate first and then go do the other. It's pretty hard to try to do them in that order, just because you're doing different things all the time. So if I subtract, subtracting 3 from my x values, so -5, -4, -3.5, subtracting 3, so that's -2.5, -2, and -1. And there's my imaginary line for the 2 branches. And then when I subtract 7 from here, get -7.5, -8, -9, and then on the positive branch, well, these values are now negative, but it's the one that was on the right side before. That's a -5, -6, and -6.5. Okay, now here's something we do special. Before we graph these points, I want to be able to graph the asymptotes. I mentioned when we graph that reciprocal function, especially when it's been transformed, we want to put the new asymptotes right away before we start putting our points, and then our points start making more sense. So what I will tell you here is the original asymptotes for the base function, and this is something we talked about when we did the last lesson. The 2 asymptotes are basically the x-axis and, sorry, where are we here? The x-axis and the y-axis. Those were the original asymptotes. The graph never crossed those 2 axes. Okay, now how do we know what our new asymptotes are? Okay, so this is me telling you what it is. The new asymptotes, if you think about it, if I had my x-axis, what's going to affect where that asymptote is? If I shift this left or right, if I shift any points left or right, is that affecting my horizontal asymptote? No, it's not. It's just keeping it where it is. But as soon as I apply a vertical translation up or down, that's changing where that asymptote will be. So that asymptote is actually the same value as the C value. So so my new asymptote will be, well, one of them will be y equals, I'll put the formula here, y equals C, x equals D. So we've already got those values, it's just a matter of plugging them in. So our new asymptotes are x equals -3 and y equals -7. Okay, now I also mentioned when we put those on a graph, we want to do like a little dashed line, because it's not part of the, it's not really it's not on the graph, but it's more of a, it's kind of like drawing the x-axis, right? But this is just as important. So x equals -3. I'm going to go back to my graph, and I'm going to put a little dotted line or dashed line, and that's x equals -3. And I'm going to do the same thing. Now this is I should have done a different scale here, but you know, sometimes you don't know what your transformations are before you do these. So I'm just going to pretend my graph is a little bit extended in both directions here. So there's that's my new vertical asymptote. That's my new horizontal asymptote based on these equations of lines here. Now, any points I put on here, if I start putting points over here, I know that I'm going to have some kind of curve here. Okay, so that's going to help me, because knowing only 3 points in each of the branches, you know, I'd probably need a bit more information, and these asymptotes are going to help. It's almost like a fence. It's saying whatever points I'm drawing, they can't go beyond the fence. So let's put the points in and see what we've got. So let's start with these ones. So -5, -7.5. So -5, -7.5 is about here. Then we've got -4, -8, and -3.5. That's really getting close to the asymptote. -9, so I sort of have to imagine -9 here. Okay, so those are 3 points. And now just imagine that I didn't draw these asymptotes, and I just said, oh, what does that graph look like? You wouldn't, probably wouldn't be able to draw the graph we're looking for. But the fact that you know that this branch is enclosed by these 2 asymptotes is going to be very helpful. So let's do the other side here. We've got -2.5, which is here, and that's -5. So that's a point right there. -2 and -6. And -1, -6.5. 6.5 right there. So you can see the curvature, and it's almost like a sort of a mirror image of these 3 points. But now that I've got my asymptotes here, I know that I can tell that this branch here is going to go up like this and down towards this asymptote. Sorry, a little, not the most steady line there, curve. And then the same thing over here, you know, this is going down that way, and this is going towards that asymptote. Okay, so that's a pretty good, the fact that we only got 6 points and are able to come up with that is pretty outstanding. But it really, you can tell it really helps by drawing in those new transformed asymptotes. And these formulas here, very easy. It's just based on those 2 values of C and D. Okay? All right, one more to go. We're going to do something with a square root function. Okay, now obviously, if we wanted to know what the base function is here, it's pretty instantly recognizable as f of x equals square root of x. Okay, I think the most difficult one was the reciprocal one, or maybe linear, but we're not doing very many linear ones, so that's good news. So if I was writing g of x in terms of f of x, well, there's my base function there, the square root. You can see, oh, we've changed the input from x to x minus 2. So I'm going to use new input for f of x. That new input will be x minus 2. So it's f of x minus 2. And then we just tack on the plus 4 that's outside the function part. So there's my kind of function notation version of g of x. And using either one of these, we're going to pull out our values of c and d. And c value, very easy, plus 4. Our d value, remember, we have to flip the sign. So it's not negative 2, it's positive 2. So we're off and running. Let's write a description of these transformations from f of x to g of x. And again, I'll combine them together. Translated, always start with that. Translated 4 units up. And 2 units. And this time it's positive, so that's to the right. Okay, so there's the description of the transformations. Let's do our base points of f of x. So this square root of y equals square root of x is our base function. And we've already done one of these. Remember, this one was 0, 1, 4, 9, 0, 1, 2, 3. Okay, so now we're going to transform those points based on our values of c and d. So this is g of x now. So what are we doing to our x values? Well, we're going to add the value of d. So our value of d is 2, so this is going to be x plus 2. I'll just put where this comes from. So y plus c, y plus c, x plus d. So y plus c would be y plus 4. Okay, and remember, our key point was that endpoint 0, 0. That should help us with the graph. We're going to add 2 to each of these x coordinates. So that's a 2, 3, 6, 11. And we're going to add 4 to the y coordinates. So that's 4, 5, 6, 7. Okay. So don't have to do anything with asymptotes because there's no asymptotes for any of these base functions except for the one we just did, the reciprocal. So then we just take these 4 points and we're going to plot them. Remember that because the 2, 4 point was transformed from 0, 0, 0, 0 was our endpoint, so that means 2, 4 will be our endpoint. So I'll graph that one first. There you go. And then we've got 3, 5, 6, 6. A little faint here. And 11, 7. I can't even fit that one on, but it's probably somewhere over there. So remember, that's our endpoint, and this continues on forever. So there's our sketch, and this is our graph of g of x. I guess I never really labeled this one. Yeah, this one, there's 2 branches. I guess we just label one branch, or both, since it is the same function. Okay, so hopefully, zoom back out a bit. Hopefully, probably the first one we went through seemed pretty tough, but hopefully by the time we got down to this one, it sort of seemed familiar and not so new to you. And hopefully, you can understand the concept, what we're doing. We're finding those values of d and c, which represent the horizontal and vertical translation when we transform a function, and then apply those values of c and d to the base points to get our new transformed graph or sketch. Okay, got some homework for you to try out. Now the next lesson, a lot of these next few lessons are all related. So our next lesson will be looking at, it's basically transformations part 2, which will be looking at stretches and reflections. Stretches also includes compressions. So those will be the only other types of transformations. And then the lesson after that, we actually put transformations 1 and 2 together, and we do examples of transformations of all types at the same time. And then I'll show you a technique that allows you to graph one of these functions very, very quickly using the same technique that we've just done here. Okay, so that's it for now. I hope you have a great day, and we'll see you on the next lesson.